Welcome to our today's lesson. We are going to discuss reflection at curved surfaces. So to begin with, curved reflectors are obtained from hollow spheres or cones. The surfaces of these hollow solids are then highly polished from the inside or outside, depending on the type of curved reflector being made. So concave and convex mirrors. So these ones are also called spherical mirrors. So types of curved reflectors. Now the first one. So the first one, we have concave reflector, or what we call the concave mirror. So it is a reflector whose reflecting surface curves inwards. So it curves inwards, as shown here where the cursor is. It curves inwards. Yes. Then it is obtained by highly polishing the outside of the glass. So outside is polished as shown. So in graphical representation, this is how we draw it. Yes, it is. This is how we represent concave mirror in a graph. Second, we have convex reflector, or what we call the convex mirror. So it is a reflector whose reflecting surface curves outwards. You can see it curves outwards. Yes. And it is obtained by highly polishing the inside of the glass. So inside is polished. Yes, as shown here where the cursor is. Then this is how it is represented in a graphical drawing. So this is how it is represent the convex mirror. The third one, we have parabolic mirror. So parabolic, it is a curved reflector whose reflecting surface curves more inwards. It curves more inwards than the concave mirror. Curves more inwards than the concave mirror, and it is highly polished on the outside. Yes, of the glass, as shown here. Obtained from a cone, it is cut, for example, where the cursor is. Then you can see it curves more. Terms that are associated with curved reflectors. So let us consider this diagram. So from this diagram, we can see the rays. Yes, the rays are here. And from there, we can see the center of curvature, the radius of curvature, the focal length, the focal point, the pole, and we can define these terms. So the first one, we have the aperture. So this is the width of the mirror. So that is aperture. Then the pole is the geometrical center of the mirror. So the pole is the geometrical center of the mirror. Then the third one, we have the center of curvature, represented by C. This is the center of the sphere of which the mirror forms a part. So the center of curvature of a concave mirror is in front, while that one of a convex is always behind. The radius of curvature is the radius of the sphere which the curved mirror forms a part. Then the principal focus, or the main axis, is the line passing through the pole and the center of curvature of the mirror, as you have seen from the diagram. We have paraxial rays and marginal rays. So we can distinguish between the two. When we are asked to distinguish that, we can just say as simple as paraxial rays are rays which are close and parallel to the principal axis, while the marginal rays are those that are parallel but not close to the principal axis. So the word but not is very important to distinguish between the two. Then we have the principal focus of a concave mirror. It is the point which all rays parallel and close to the principal axis converge. So for a concave mirror, it converges after reflection. For the convex mirror, it diverges from after reflection. It diverges from that point after reflection. So we find that the principal focus of a concave mirror is always positive. The rays actually pass through it, so it is real. That is, it is positive. Then the principal focus of a convex mirror is always virtual. The rays, because reflected rays only appear to pass through it. Focal plane. So to understand focal plane, you can see from this diagram. You can see from this diagram The rays are coming from infinity, obeying the laws of reflection. So the image is formed at F. So here, so that line passing through F, and that is what we call the focal plane. So we can say this is the plane perpendicular through the principal axis and passes through the principal focus. So that is it. For a concave mirror, parallel rays which are not parallel to the principal axis converge at that point. That point, that is the focal plane after reflection. Then for a convex mirror, parallel rays which are not parallel to the principal axis, we call them the marginal rays, appear to emerge from that point after reflection. We find the focal length is the distance from the pole of the mirror to the principal focus, represented by letter F. So here is a point to remember. In optics, full lines represent real rays and object, while the dotted line represent virtual rays and images. Let us now move to the relationship between the radius of curvature and the focal length. The relationship is just simple. Find that the radius of curvature is twice the principal focus. As simple as that. On Earth, we only have two laws of reflection. The two laws are obeyed by the curved mirrors. The first one, we have the angle of incidence equals to the angle of reflection at the point of incidence. Then we have the incident ray, the normal, and the reflected ray all lie on the same plane at the point of incidence. So those two laws are very important. Those are the two laws that we have on Earth, the laws of reflection. If you conduct the experiment, you can come with yours. You'll be welcomed. But for now, we believe in the two laws. Let us move to ray diagrams. Yes, in ray diagrams, the ray diagrams are used to show and explain images, how the images are formed by curved mirrors and their characteristics. So we have the rays that we always use. So we have the four major rays. So the first one, we have a ray close and parallel to the principal axis. As shown, the ray is close and parallel. You can see for a concave mirror, it is reflected through F, as shown. That is for a concave mirror. For a convex mirror, it appears to diverge from F after reflection. Then the second ray, we have a ray through the principal focus of a concave mirror. Yes, so a ray through F. Remember, when we were discussing about the rays that are close and parallel, we saw that it is reflected through F. So the opposite. So when a ray passes through F, it is reflected close and parallel for the concave mirror. Then for the convex, when it passes through F, it appears to be reflected close and parallel. Then the third ray is a ray through the center of curvature. That is a ray through C. We say that this ray obeys what we call the principle of reversibility of light. Yes. So it retraces that path. It is reflected along the same path. As shown here, it is reflected along the same path. Yes. The fourth one, we have a ray at an angle. So a ray at an angle, following and obeying, believing and trusting the laws of reflection. We find that they obeys the laws of reflection, and on Earth we only have two. So the angle of incidence equivalent to the angle of reflection. Yes, the incident, the normal, and the reflected all lie on the same plane as at the point of incidence, as shown for the both concave and convex. Let us now move to the characteristics of images formed by curved reflectors. To start with, we'll commence with what we call a concave mirror. So the first one, object at infinity. Yes, I remember this one we used to discuss the focal plane. So rays are coming from infinity where the object is, following the laws of reflection. So the angle of incidence equivalent to the angle of reflection. So when that one is obeyed, we find that the image is formed at F. Yes, considering and comparing the size of image and that, we can find the properties. So the first one, the image is real. It is formed in front of the mirror. So second, the image formed at F, at the person it is formed. It is inverted. You can see it is upside down. Then it is diminished or smaller than the object. Second, we have object at C. Object at C. Yes, we have this one. So the first ray that we use is a ray close and parallel to the principal axis. So it is reflected through F as shown. You must show the arrows where the rays are moving. Then the ray through the center of curvature reflected close and parallel. So you can see the object is still formed at C as shown there. So the image is formed at C as shown. Sorry for that. So image formed is at C. It is real formed in front of the mirror. It is inverted, yes, and it is of the same size as the object. Therefore, we can say the magnification is what? Is 1. Yes. The third one, object beyond C. So when object is beyond C, we can use two rays. So the first one is a ray close and parallel. It is reflected through F as shown. Remember, don't forget to indicate the arrows. Then array through F reflected close and parallel. Then compare the sizes and get the properties. So the first one, the image is diminished. It is smaller than the object. Second is real. It's formed in front of the mirror. Then the third one, it is inverted. It is upside down. Yes. It is formed then between C and F. What about object placed in between C and F? So it is the opposite of this. Let us see that. Object between C and F. Yes, I said it is the opposite of object placed beyond C. So you can see it using two rays. Rays close and parallel and a ray through F. Remember, a ray must come from the head of the object. So it is reflected close and parallel. Then the image is formed here. You can compare the size. Now the image is magnified. It is inverted. Yes, it is real from B, then from beyond C. Those are the properties. Then object at F, yes. So remember, when we were discussing the rays coming from where object is at infinity, the image was formed at F, and we use it to define the focal plane. So therefore, when the object is now at F, meaning the image will be formed at infinity, so we can get the properties when you draw that one keenly. So it is formed at infinity, it is magnified, yes, then it is real. So those are the properties that we can get. Object between F and P. So object between F and P, first of all we use ray close and parallel. Yes, you can see the rays up, then a ray through center of curvature. So when you extrapolate, you find the image is formed behind the mirror shown here. So this is a special case. Yes, you can compare the size. We get the properties. It is magnified, it is upright, then it is virtual, formed behind the mirror. Yes. After discussing all those of our concave mirror, I think you are able to remember how we draw them and remember the properties, how we identify them. Let us now move to convex mirror. So in convex mirror, irrespective of the distance of the object in front of the mirror, the image formed by convex mirrors are always upright, smaller than the object, and is formed between P and F. So irrespective of the distance here, the image is formed between P and F. It is smaller, it is upright, it is virtual. So those are the properties. We can consider this example. A lady holds a large concave mirror, focal length 1 meter, 8 centimeter from her face. So use a scale. So you've been told a focal length. So distance from here up to here is 100 centimeter. Yes, according to the scale. Then this one from here up to here is also 100. Distance between C and F equivalent to the distance between F and P. Yes, this one is a symbol for concave mirror. So it is just an object between F and P. So we find from the special case which we said, which is shown here, this one, yes, this, you can see where the image is formed. So if you draw that one keenly, it is there. So the characteristics, the image is upright, it is magnified, it is virtual, then formed behind the mirror. Yes. Let us move to the graphical construction of ray diagrams. Find that the images are drawn to scale in a ray diagram, and this is the best done on graph or linear paper. So before we draw, let us discuss the magnification first. So magnification is the ratio of image height to the object height. It can also be defined as the ratio of the image distance to the object distance. Yes. Then the ratio image height to the object height is the magnification. Therefore, is equal to image distance divided by the object distance. This one can be used calculate as substituting the formula and making what the subject get. So we can consider this one as our first example. An object 3 centimeter high is placed 6 centimeter in front of a concave mirror of radius of curvature 10. By scale drawing, determine the position of the image, size of the image, nature of the image, and magnification. So when you draw using the scale, so we have this one as the concave mirror, yes. Then F is here. Consider the scale that we've used, where we say 1 centimeter represents 2. Yes, 1 centimeter represents 2, the smaller ones. So when you draw keenly, you get the object image being formed somewhere here. So you can now get the position of the image from the mirror. So that one, it is 13.6 times 2. According to the scale, you get 27.2 centimeters from P in front of the mirror. Yes, we get 27.2 centimeters. Then the size of the image, now this one from here to here, it is 6.6 multiplied by 2. According to the scale, get 13.2 centimeters. The nature of the image, so you can see it is magnified. Yes, it is real, form far beyond C. Yes, so it is inverted. So those are the properties. Then the magnification. The magnification is the image height to the object height. So when you substitute that one, get that 4.4. A convex mirror, the second one, the convex mirror focal length 15 centimeter produce an image 10 centimeter away from the mirror. If the image is 3 centimeter high, determined by scale drawing the size of object distance, object height, then the magnification. So when you draw this one is a convex, yes, you can see the focal length is behind the mirror, yes, like that. So a scale we use, sorry for that, yes, the power was misbehaving, but I've corrected that. So we've used a scale of 1 centimeter represent 5 centimeters. So when you draw that one, can you remember this one is for convex mirror. So we said that irrespective of the distance, the image is formed between F and P. So when you use rays accurately, you get object to be around here. So we can get the object distance. So object distance 1, 2, 3, 4, 5, 6. Then we multiply by the scale that we use. So we get 30 centimeters. Then object height. So it is 1.4. Yes. So 1.4 times 5, we get 7 centimeters. So magnification is the image height divided by object height. 3 divided by 7, you get 0.423. Let us now move to the mirror formula. So the object distance, the mirror formula, we consider object distance for focal length and that. So it is said that 1 over f equals to 1 over u plus 1 over v. Yes. So that is the mirror formula. Therefore, we can play around with the formula, multiplying all through by v. We get v over f equals to v divided by u plus 1. But v divided by u is the magnification. Therefore, v divided by f get magnification plus 1. Then we can play around with that. Let us now move to the real is a positive convention. So this is a sign convention used in mirror formula in order to determine the position and the nature of the image formed by curved mirrors. So according to the real convention, we say that all distances are measured from the mirror as the origin. The distance of real objects and images are considered positive, that is for concave mirrors. The focal length of concave mirrors is therefore positive. Then the distance of virtual objects and images are considered negative. That is for convex mirror. The focal length is negative. So you have to remember this. Very important. You have to remember that it's negative for that. Then also you have to remember this when you're working. You have to remember the focal length of a concave mirror is positive and focal length of a convex mirror is always negative. So let us consider this example. So an object is placed 10 centimeters in front of a convex mirror. So remember it is a convex, so focal length is positive, concave, yes. Focal length is 20 centimeters. Determine the position and the nature of the image. So when you substitute making 1 over v the subject, you get negative 20 centimeters. So you can tell it is diminished, it is virtual, all that. You can work out this. A concave mirror with radius of curvature this produces an inverted image. Yes, as that. It is not challenging, but you just draw accurately. Then you get the object and the image. Yes, I hope you will draw that one. Let us now move to graphical analysis of the mirror formula. Yes. So the first graph we are going to analyze the graph of u 1 over u against 1 over v. So where we have 1 over u on the y-axis and 1 over v on the x-axis. So when you draw this, you find the graph is a straight line having a negative gradient. Yes. So either x or y intercept is equivalent to 1 over f. Yes. From the mirror formula. Then second graph, we have a graph of uv against u plus v. So from the mirror formula, we can work that one out. 1 over f equals to 1 over u plus 1 over v. Then working with the LCM, we get and making uv the subject of the formula, we say uv is equals to u plus v, everything divided by f. Yes, everything here we divide by f. Yes. So that graph is a straight line from the origin, shown here. It is a straight line from the origin. Then its gradient is positive. Therefore, its gradient is what we call the focal length. Yes. Third graph, you have a graph of m against v. So this we just analyze the mirror formula. So from the mirror formula is 1 over f equals to 1 over u plus 1 over v. Multiplying all through by v, we get v over f equals to m plus 1. Where I said we always get v over f equals to v over u plus 1. So that v over u is the magnification. Yes, we get that. Then making m the formula, you get magnification is v over f plus or v over f minus 1 when you make magnification of the subject. So that graph is a graph which has y-intercept as at negative 1. So we get the gradient, though not gradient, but what we call the magnification is equals to negative 1. Then this one at the x-intercept is what we call the focal length. This one is what I will explain. Therefore, a graph of m against v is a straight line with a gradient and is negative 1, which is also called 1 over f. M-intercept is v, all that. Let us now move to the applications of curved mirrors. Applications of curved mirrors. So the first one is for concave mirror. So where do we use concave mirror? So the first one used as shaving mirrors. Why are we using this one as shaving mirrors? So we use it because they produce magnified and upright images when the object is between the principal focus and the pole. So when you have the object between the principal focus, we say this one is a special case in concave mirror. So you find that the image is formed is always upright, diminished, and virtual. So the concept is also applied by the dentist when examining the teeth. So the reason is that they produce magnified and upright images, just as this. So the third application, we have used as a reflector behind projector lamp to reflect light traveling away from the projector. So we have this one, it reflects light traveling away from the projector, as shown here. The lamp is placed at the center of the concave mirror. The fourth one is used in telescopes to bring distant objects like stars at the focal point. So these ones are objects at infinity. We always use those rays that hit the mirror at an angle, so they obeys the laws of reflection. So object is brought to the focal, the image of that object is brought to the focal point as shown here. We use a solar concentrator to bring light energy into focus, still the same concept. Yes. After discussing all those applications of curved mirrors, the concave mirrors, I hope you'll be able to remember they are just 5 simple ones. Then let us now move to convex mirrors. So convex mirrors, we have the first use as a car or motorcycle side mirrors because they form upright images and have a wide field of. So these two reasons are very important. So these two reasons are the reasons why we use them. You can underline them in your notes. They form upright images and have a wide field of view. That's why they are used as side mirrors. I hope you have ever bought a vehicle. You see the driver always use those side mirrors and they want to overtake all those. So because it is used to make the mirrors because it has a wide field of view and it forms a wide upright images. Second, use in supermarket to monitor movement of customers. So the reason are still these ones have wide field of view and also form upright images. So you can see it has wide field of view here than plain mirrors. So we have to remember that these mirrors, the marginal rays are not brought into focus at the focal point, not brought into focus at the focal point, resulting to the blurred images, which is the defect called the spherical aberration. Yes. So this is a defect of these mirrors. Therefore, we can move to what we call the disadvantage of convex mirrors. We always know that whatever has advantage has disadvantage. So the disadvantage of this is that it forms a diminished image, diminished small size than the object, uh, giving a wrong impression to the driver of the vehicle behind it. So it doesn't tell the actual distance where the object is or where the another vehicle is. So it gives a wrong impression, which can result into an accident. Let us move to parabolic mirrors. So parabolic mirrors used for propagation of parallel light beams of high intensity, like in hand torches, satellites, and headlights. So this mirror is just used to solve what we call the spherical aberration. It's used to solve the problem of the spherical mirrors, what we call the spherical aberration. So it is unlike the concave mirrors, which all the marginal rays are not converge at principal focus. The parabolic mirror converge all rays parallel to the principal axis and incident on its surface at its principal focus as shown. So parallel rays start and that. So we find it is at F. That yes. So this is now the defect. This one is a concave mirror. You can see the rays are not brought into sharp focus. We have focus here, we have here. So it is not brought into focus. But for parabolic mirror, all the marginal and paraxial rays are brought into sharp focus. So that is the end of the topic or the end of the lesson. I hope you've enjoyed the lesson. So thank you for watching. We are committed to serve you with the best, and also welcome to this our YouTube channel. We call it Physics Discussion Forum. Don't fail to subscribe, like, comment, and share. Thank you.